So this is the 12th session on signals and systems, and what we are going to do is to study time shift for discrete signals and time inversion or reflection. Understand that time shift for continuous time signals we had done in the last session. So in this session we are going to study time shift for discrete signals. However, inversion we have done for none of them, that is neither continuous time or discrete time. So after doing the first one, then we are going to study inversion in general and then see its implementation for continuous time as well as discrete time. Okay, so let us start. So time delay for discrete signals. So in this case, let's say there is a system which provides the delay, and input to that is a discrete time signal which is xn. Note the change in the independent variable here. It is n, which is going to be an integer, whereas in the case of a continuous time, that was t, and that was represented by floating point variable. All right. So the output from this system will be written like this, where n denotes the number of sample points. So as in the case of a continuous time signal, here also the entire waveform will shift to the right. But in the case of continuous time, we said delay was 3 seconds or 3.5 seconds or whatever. In this case, the delay is going to be in terms of an integer because it will be delayed by so many number of samples, capital N number of samples. And as in the previous case, here also the waveform will shift to the right by n samples. So let us see an example of this. Suppose our xn is like this, okay. It remains 0 right from -10 up to -4. Thereafter it increases linearly, and then from 6 to 10 again it is 0. So if we delay this waveform, then each point on the waveform will shift to the right. So let's see that. Look at this point here. When n is equal to 5, you get the highest amplitude here. So since the whole waveform is shifting to the right by 3 samples, note this is x n minus 3. Therefore this 5 will now correspond to t. So this will occur 3 samples later. So this occurs at 8. This is 5 gets shifted to 8. 4 will get shifted to 7. So note this 6 and 7. In short, every point shifts to the right. And this is what happens when you provide the time delay for the discrete signals. Okay. So let us now write the program for this. Oh, okay. Before doing that, let us discuss the time advance for discrete signals. So here the notation is x n plus n. Remember, for delay, we had written x of n minus n. In this case, it is n plus n. So in this case, the waveform simply shifts to the left by n samples. And note that as in the case of continuous time, here also, this is not possible to execute in real time. Waveform can be advanced only if it is in the stored form, because in real time, you can't really go back in time. So you can't do this in real time. However, so whenever people talk of time advance for either continuous time or discrete time signals, they are referring to stored signal. Okay. So again, note in this case that sample number 5 has the highest amplitude. Now this is advanced by 3. So 5 minus 3, so 1, 2, 3, this occurs at 2. And in fact, every other sample shifts to the left. That is your time advance. Okay. Now the shift function we had studied last time, the same shift function we are going to use for discrete time signals also. Only thing is that our parameters that we are passing in the previous case, this was a floating point variable. These were all floating point variables. But whereas in the case of discrete, you will find that this x will be floating point, but t is going to be an integer, and d also is going to be an integer. These are the passing ones. So the function essentially remains same. All right. So to study the calling program for this, let us first of all generate some signal. So the first few statements that we'll study in this program are directed towards generating the signal itself, and then it will call the shift function and generate the shifted one. So clear CLC, CLF as usual. N is -10 to +10. Default increment is 1, so I'm not writing it here. -10 to +10. So basically we are talking about 21 samples. So since our independent variable has 21 values, the dependent variable that we generate also must have total number of 21 values. Then only we can plot one against the other. So first what do? We generate a part of the waveform. So zeros 1 to 6. So that means first 6 samples are 0. The next two is lin space from 0 to 5. So it starts from 0 and increases linearly up to 5 amplitude. And how many such samples? Total number of samples are 10. So mind you, the first segment has 6 samples. The second segment has 10 samples. So now the third one must have 5 samples in order that the total are 21. So the third one again we say zeros 1 to 5. So I got total number of 21 samples. And now I can generate my signal by simply putting these sequences one after another. So I say X is X1 followed by X2 followed by X3. I have got my X. So now what I do, I use the shift function in order to obtain the shifted one. And note that in this case we have provided -3 sample of shift. So negative for the shift function, remember, it means advance. If this was plus, it would mean delay. This is somewhat different than one of the earlier functions that we had studied for ramp delay, etc. But the shift function works like this. So if this is positive, it will be delay. If it is negative, it is advance. So now that you have got your X and Y, so X is obtained here, Y is obtained here. So you can plot both of them as function of N. And when you do that, this is essentially generating the same signal that we have discussed in the previous slides. So again you get the same result here. This is what you expect and this is what you get. So this is advanced by 3 samples. So this is 5 minus 3. So it's advanced by 3 samples. All right. So this gives you some idea about what is the meaning of time shift for discrete signals and how do we implement it through programming. Okay. Now we are ready to study another operation on signals. This is called as time reversal. So what is the notation for this? This is input signal to the system which is performing inversion, let us say, is xt. And the output from that is x of minus t. And what is the meaning of this? It's essentially, suppose you plot xt as a function of time and then rotate the waveform around the y-axis. Okay. Then you will get x minus t. And you rotate it through 180 degrees. So essentially what you are doing is you have got an increasing sequence from left to right. When you flip it, when you reverse it in time, it will be, if this is increasing from left to right, then after flipping it will decrease from left to right. That is what will happen. Or another way of saying is that you are rotating the signal through 180 degrees around the y-axis. So rotate around y-axis by 180 degrees. And note, this is also not possible in real time because then you are asking some of the samples which are present now to be generated earlier. You can't go back in time. So obviously time reversal also can be performed only on signals which are first stored in the memory. Then they can be performed. So let's see. Right now understand we are talking about the continuous time signals and the nature of the variable should make it clear to you anyway. Consistently we have been using t for continuous time and n for discrete time. So right now we are talking about the time reversal for the continuous time signals. And let us say we got a continuous time signal like this. So right from -10 up to -2, this 0. From -2 to +1, it increases linearly, then it decreases linearly all the way up to 5. So what do you expect? Now if you rotate this around the y-axis, this is my y-axis, then what will happen? This point which was corresponding to plus 5 will now correspond to minus 5, and this point which was corresponding to minus 2 will now correspond to 2. Okay, so either you think of rotating around the y-axis, or you think of reading in the reverse direction and then putting in the values. Whichever way, you will get this waveform. So instead of ending at plus 5, okay, it starts from minus 5, and instead of starting from minus 2, it ends at plus 2, and these are the values. Okay, so this is what we mean by the time reversal. Don't confuse this with the amplitude inversion. Suppose you got some signal xt and you multiply it by minus 2. What it means is that every amplitude simply reverses the sign, which is not the same thing that is happening here. Note that whatever amplitude you have got, that remains same, only the time at which it occurs is going to be different. So that should not be confused with the multiplication by a constant which is negative. That is different, and time reversal is different. Okay. Now how to do this time reversal? So in MATLAB this can be done easily. You got a statement which is called as a flip left to right. So whatever numbers you have from left to right, they are flipped. So they will reverse their order. So in the console, if you type this a equal to 1 to 6, you will get numbers 1, 2, 3, 4, 5, 6. Then use this particular function, which is a built-in function in MATLAB, which says flip LRA, that is equal to B. So you get exactly, so 6, 5, 4, 3, 2, 1 now becomes 6, 5, 4, 3, 2, 1. Okay, so all you have to do now is to first generate the waveform and then use the flip LR statement in order to provide the time inversion. So all this now generation of the waveform, this particular waveform we have studied in the last session. So I'll not go too much into the details of this. So you generate R1, R2, R3, then you take sum of all this, you call it R. But while displaying, since we were all the time talking about X, we can display it as X. It doesn't really matter as long as you understand what is happening. And then what you do? Then you generate Y by using the flip LR statement. So you now have R and Y and you can plot them. So you can plot them here, and then you can see you get it like this. So this is my input to the system which is doing time inversion, and this is the output. As you can expect, the whole thing is rotated by 180 degrees. So whatever was the amplitude at plus 5, now you get it at minus 5, and so on. So this is your time inverted signal. Okay. What about time reversal for discrete signals? Again, very similar. Instead of t, you now have n. So input is xn, output is x of minus n. And again, for discrete signals also, for the reasons that we have discussed, again, this is not possible in real time. And you can now see that if you generate a signal like this, you're getting a maximum value of xn at n equal to 5. So when you flip the waveform, when you time invert, there are a number of terms which are used. So time inversion is one term used, folding is another term that is used. So what is the maximum value here is at plus 5. Now in the inverted waveform, it will occur at minus 5. So this is how the time inverted waveform will look like. Okay. Now the program is again simple. So in this case, what we have done, we have not used any RAM functions, etc. We have simply used zeros and linspace in order to generate our discrete time function itself. So it's easy to see what it is. N equal to minus 10 to plus 10. Then use zeros 1 to 6. Okay. Then x2 is linspace 0, 5, 10. In fact, the same program that we have seen earlier when we were talking about the shifting. So it is the same way the x is generated, But then we had said y equal to shift of x. Instead of that, we are saying y equal to flip LR. So it will perform the folding, or it will perform the time reversal, and then it will plot this. So again you can see that this is at +5 instead of that starting from -5, and here it was increasing, here it is decreasing. So in this session we have studied how to do time shifting for discrete time signals, because last time we had studied only continuous time, and then we have studied time inversion for both continuous time and discrete time signals, and that's all in this session.